we meet under less than ideal circumstances. But thank both you and Matthew for making all those videos possible. We moved to do it quickly at the beginning of the spring break because we didn't know what will happen. And we recorded everything in my office. There were lots of videos recorded on the same day. In fact, we had 2 days before the whole thing was closed. On Thursday after our class, we started to record until late, 9, 10 p.m. And then we did the same thing on Friday. So I guess we got tired. I have to apologize to all those who are listening, will watch this video. Maybe there are inaccuracies here and there, hopefully not much, not a lot. But I also looked at myself. It's all nice when you look at yourself and you've never done this before. I don't recognize my voice. I didn't know that I'm making all these gestures and so on. But so I apologize for these things. Now, I thought that it's maybe good if you can record something from distance. I wanted to say a few more things about quadratic residues, non-residues than I had a chance that day. And also about sums of two squares in this same video. But before I start talking about how all of us were tired at the time, but it's nothing compared to what happened to me some long time ago. Very short story, but true. In 1999, that academic year, 1998-1999, I had a visiting position at McGill University, that's in Montreal in Canada. And so I was teaching several classes, some of them at McGill, other classes at Concordia University. That's another university in Montreal. One day I was so tired, I just returned from a trip to the United States. Actually, I came here for a job interview and went to several other universities for job interviews at the time. And so I arranged so all of them were immediately one after another. There was no time for me to sleep. Even when I returned to Montreal that night, there was no time to sleep, and in the morning I had the class. It was a calculus class. Class was larger than our class. We have like 31 students in our class, but then there were about 70, 75 in that class. So I go to class, still tired, and I start to teach. I say some things, write on the board, work on some examples, calculus problems. And then in the middle of the lecture, I said something, and then it didn't feel right. Something that I said made me worry a little bit. So before I continued, I double-checked the actual mathematics that the statement that I made. I realized that the statement was fine mathematically, but what happened, there was something wrong. It was not mathematics. It was the fact that I said it in Romanian. I apologized immediately, and I restated it in English, and then I went to the board to write this statement on the board and then to look at some examples. And when I look at the board, the entire blackboard was written in Romanian. Now that's in the middle of the lecture. I, of course, apologized. I erased everything and I started the lecture from the beginning, this time in English. What's so funny is that you have 70 people there and not a single one told me for the first 20, 25 minutes that I'm talking in Romanian. They were taking notes. That was very serious, taking notes in a language they don't understand. So that was the funny thing about that. Now, back to this quadratic residues. What we talk about right now has nothing to do with the actual problems. It's not helpful for the problems that will appear on exam next week, third hour exam next week. But it's a very nice property. We discussed this, we use it on problems on the exam, but we didn't prove this. Not the quadratic reciprocity, that's the deepest of them all, that will require a lot more time. But I won't go into the proof of that one. But the fact that the Legendre symbol is multiplicative, that's the thing that I wanted us to prove right now. Now, I don't have the blackboard here, but you said that you can type some things. All right. Can you show us a screen? All right, quadratic residues and sums of two squares. So, suppose P is a prime number. Right. So suppose P is a prime. We just say P prime. Now we know there are exactly P minus 1 over 2 quadratic residues and P minus 1 over 2, let's say P minus 1 over 2 QNs. This is quadratic capital Q, capital N. For us, it's quadratic non-residues, and capital Q, capital R, quadratic residues. And the proof goes like this. Now, what we need to do is to prove the following. QR times QR equals QR times QR equals QR. By this, we mean the following. Equals QR again. If I take a quadratic residue, I multiply by another quadratic residue, not the same one, I get a quadratic residue. And then it means that if the Legendre symbol for the first number is +1, that's when this is a quadratic residue. And the second number has a quadratic symbol that's +1, then the product also will be a quadratic residue, and the symbol will be +1. Then we need to show that when the symbol is +1, the other one, the symbol is -1, the product of the two numbers, the symbol is -1. So we need to show actually what this means is that if I take a QR times, so let's write on another line, QR times QN equals what? A QN. That is to say, anytime the first number is a quadratic residue and the second is a quadratic non-residue, the product will be a quadratic non-residue. Then similarly, a QN times a QR will always be equal to a QN. These are all quadratic residues modulo the same prime number. And lastly, a QN times a QN, that is to say, a quadratic non-residue times a quadratic non-residue we need to show that it always equals a quadratic residue, equals a QR. Because if you think about the first number, this QN is in fact our number A. If A was a quadratic non-residue and B is a quadratic non-residue, then A times B has to be a quadratic residue because the quadratic symbol of A is -1, the quadratic symbol of B is -1, then the quadratic symbol of A times B has to be the product. That was what we wanted to show. So -1 times -1 has to be +1. So we need to show that it's a quadratic residue. All right, there's a nice idea behind it. First of all, the only easy or extremely easy of these statements, these 4 statements above, is the first one. And it says the following. Say if little a is a QR, A is a QR, little b is a QR. Okay, we need to show that A times B is a QR, is a quadratic residue. A QR, a quadratic residue. Now, how do we show this? We look at the definition of quadratic residue. A is a quadratic residue means that A is congruent to a square. So we can write A is congruent, a little a, okay, same number, is you can put equality if you cannot type congruent, but A equals a square, n square. Can you put an n square? N square mod p. Okay, let's write under this relation b equals another square, because b is a quadratic residue, so it's equal or it's congruent to a square, say m square mod p. Now we know if we have congruences, we can multiply the two congruences. So let's see what we get on the left side is just a times b. Plus a times b equals, and it's n squared times m squared, but this is the whole quantity is the n times m, yes, this quantity squared, mod p. So it shows that indeed a times b itself is congruent to a square. So it's a quadratic residue. Thus, a times b is a QR. Now, the rest of the proof, let's not write anything, but let's think. Just let me see how I do this. It goes like this. Let's recall that if I take all the numbers from 1 to p minus 1, suppose, and let's just say we work on the second one. So the second one, let A be a QR, little a be a QR, and let little b be a QN, a quadratic non-residue. Then show that a times b is a QN, is a quadratic non-residue. Now, how do we show this? Let's recall when we proved, say, Fermat's little theorem, and on other occasions, we notice that we can take a number a, the relatively prime with p. Don't type anything. Just take a number a, little a, and we can multiply all the numbers from 1 to p minus 1. Look at their remainders modulo p, and we found that they are exactly the same as the numbers from 1 to p minus 1 in another order. That was our proof of Fermat's little theorem, because then we took all these congruences, we multiplied the congruences, and we got a to the p minus 1 times 1 times 2 times 3 times p minus 1 is equal to 1 times 2 times 3 times dot 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 p minus 1 in another order. And we cancel this 1 times dot 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 p minus 1 on both sides, and we got a to the p minus 1 is congruent to 1. Okay, let's only take part of that proof, which show that when I multiply all the numbers from 1 to p minus 1 by little a, I get again all the residue classes or all the congruence classes from 1 to p minus 1 in another order. Now, right. It's in fact a times 1, comma, a times 2, if you want to put it like this. Yes, that's how we should say it. A times 1, it's the first number, comma. The second number is a times b. So a times 1, a times b times b. No, sorry, not a times b. A times 1, a times 2, a times 3, a times p minus 1 are the same as the number. So a times 1, a times 2, and so on. Yeah, a 2a, 3a, yes, it's better like this. The last one being p minus 1 times a. Right. Yes, they are the same numbers as 1, 2, 3, p minus 1, 1, comma, 2, 3, up to p minus 1 in another order. Okay, so now what's the main idea? We assumed, but don't write now, please don't write anything else. So we can focus on what's written. We assumed above, you see part 2, that a, little a is a quadratic residue. Now, just look at these numbers, a, 2a, 3a, p minus 1a. And we know that our little a is a quadratic residue, our assumption right now. So we took a quadratic residue, that's this a, and we multiply all these numbers, 1, 2, 3, up to p minus 1. half of them are quadratic residues. Those half of these numbers that are quadratic residues are multiplied by our little a, that's a quadratic residue. And we just proved above that when we multiply two quadratic residues, we get a quadratic residue. So this means that half of those numbers on the left, A2, A3, A, are half of these numbers, 1, 2, 3, up to p minus 1, are multiplied by A. Those that are quadratic residues are multiplied by A. A is a quadratic residue, and will give us all the quadratic residues that are on the other side that you wrote at the end of this row, 1, 2, 3, up to p minus 1. It follows that the remaining numbers, and these are the quadratic non-residues times A, have to be equal to the quadratic non-residues in another order. So that is the whole idea. Similarly, if you take a quadratic non-residue and multiply by the quadratic residue. Now, I ask you just before we started to record this to show this, compute all the products of numbers, say mod 11. Do you have that on another screen? So it's, in other words, it's a multiplication table mod 11. Can we see that screen? All right. So what this is, you take the numbers from 1 to p minus 1. This means 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then on the first column, 1, 2, 3, up to 9, 10, up to 10, and you multiply them. So let me check that you did it properly. 3 times 5. 3 times 5 is 15. But modulo 11, subtracting 11, is 4. Okay. So these are the, this is the multiplication table modulo 11, basically. Now, I wanted to check, first of all, that when I take a quadratic residue times a quadratic residue, that's the first thing we said, it's a quadratic residue. I wanted to use two colors, and you said that you are able to do this. But let's first find the quadratic residues. How do I find the quadratic residues if I already have the multiplication table? It's very easy. I just look at the diagonal. Because the diagonal is a number times itself. So these are all the squares. So these are all the quadratic residues. So in other words, numbers on the diagonal are all the 5 quadratic residues. We know there are 5 quadratic residues, 5 quadratic non-residues. And if I read from the, on this diagonal, I have 1, I have 4, that's a quadratic residue, 9, 5, and 3. 5 squared is 3. And then, of course, as we know, 6 squared, 7 squared, and so on, give us exactly the same numbers, the quadratic residues, in reverse order. So after 3, you'll get another 3, and then a 5, and then a 9, and a 4, and a 1. Now, can you do the following, please? Can you take another color? Say like the green color. The green color.
Okay.
And these numbers on the diagonal, make them green. Can you, not only those on diagonal. I realize they will take a few minutes,
No.
but can you make them green? You can make them green at the same time. Is this green visible or not? Okay, let's say it's visible. Now, okay, now, what are you doing? There's still green. I hope that we can see it in the video. Okay, now, on the first row above, I want to know the quadratic residues. We already know that quadratic residues are, so these numbers 1, 3, 5, 1, 3, 4, 5, and 9. Can you make them green? Not that row, the first row, the one above. Yes, green. The quadratic residues. All right. And the same on the first column. Okay, now, we proved one thing before, that when you take two quadratic residues and multiply them, product is a quadratic residue. Let's check this. That anytime you take a green number and then a green number, you get green. You see, or maybe we'll allow you first to do this everywhere in this, not everywhere on this table. Yes, right here. When you take a green times a green, it's green, and you can make them green. Just the green times the green. 3 times 5, you forgot, that's a 4. It's green. Yes, it's still green. And everybody can check, everybody who's looking, who's watching, they see that indeed. That was easy to show for us. Okay, so can you make all of them green? Okay, now, this means that if I look at the row of 3 times this one, 3 times anything that's green is green. Now, what I'm saying above is, if I look at a row of 3, I have all the numbers from 1 to 10 in another order. I have them 3 times 1 is 3, 3 times 2 is 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 1, and so on. So I have these numbers 3, 6, 9, 1, 4, 7, 10, 2, 5, and 8. These are all the numbers from 1 to p minus 1, so from 1 to 10 in our case. But already on this row, we have 5 green numbers. They appear when I multiply my number that was green, that's 3, by any green number. And we got 5 numbers. All of them are green. So it means that the other numbers are not green. Let's use another letter for quadratic non-residues. Do you have another letter that another color that's easily visible, like a red? Do you have a red? Yes. So you first do 2, 6, 7, 8, and 10. Let's make those red. On the first column only. All right, make them red. And now let's go back to our green row, which means it's not fully green. It's 3 times. 3 times anything that was green is green. Well, this forces 3 times anything that's red to be red. So let's make those red. Just on the row of 3. 6 is red. You can see 6 is red above. 6, 7, 10, 2, and 8. Let's make those red. Just do that. So again, why these 5 needed to be or have to be red is because you already have 5 green numbers on that row. And we have all the numbers from 1 to 10 on that row. And we know that half of them are quadratic residues, half of them are non-residues. So we do have to have those 5 that are non-residues, quadratic non-residues right there. Now the same holds true for every green row. So now we can make more red numbers.
Can we keep them black instead?
Well, I wanted to make one more point. That's why let's make this red.
So this one?
Yes, just those that start with a green. Yes, when you take a green row, and everybody can check that these are all the time the same numbers that are the quadratic non-residues, 2, 6, 7, 8, and 10, in another order. Yes, the first row as well.
This one?
Oh, yeah. Okay, yes, that's the row of 5. And then we have 2 more rows, the row of 1 and the row of 9. That has to be red. Okay, and the row of 9. Let's make them red. Okay, now by symmetry, same thing happens when I take a green column. Say the column of 3 instead of, let's look at first the column of 3. Because there was the row. It's exactly the same thing that happens on columns. So now this can be made red, same red. Okay, so now we go with columns. And exactly the same for green columns, just green columns. So this other part is by symmetry. And then also the column of 1. All right. Okay, now there are still some numbers that are black. And this is the final nice idea in the proof. We saw that a green times a green was a green. Then we realized that a green times a red has to be a red. Then by symmetry, a red times a green has to be a red. So now we are left with a red times a red. Only red times red is left black at this moment. You can see a red times a red is still black. What I'm trying to say is that these numbers are forced to be green. Why? Because if I look at any red row, say the row of 6, I already have all these quadratic non-residues, because they came when I multiply my 6 that's red with anything that was green upstairs, 1, 3, 5, and I got red. So it means that I got all the 5 red numbers that are possible on that row. So the remaining 5 numbers have to be green. So now we can make them green, and indeed they are green. But that's the reason. There's the proof that they have to be green. And then the same happens now for every red times red. So again, this is kind of a proof that the main ideas of a proof. Why this Legendre symbol is multiplicative. So a quadratic residue times a quadratic residue is a quadratic residue. So green times green is green, green times red is red, red times green is red, and it follows then the red times red is green. Now, when I compute in a problem the Legendre symbol, any red number here, the Legendre symbol is -1. Legendre symbol mod 11. And any green one, the Legendre symbol is 1. So we have multiplicativity of the Legendre symbol by what we just did.
Okay.
Okay, so let's start with this.
To,
can you tell me how long this?
Yeah,
video?
so we'll make another video after this. Yeah.
Oh, this was too long?
No, we can stop at this point of time. Or do you want to continue?
Well, let's continue, because the other thing is also quick. It's just a small proof.
Sure.
I wanted to just show one thing. Why is it that if I have a prime number, the prime number is not a quadratic, the prime number is not representable as a sum of 2 squares if the prime is congruent to 1 mod 4. I'm sure we saw this before, but we can see it quickly. But the other more interesting part is, why is it that if the prime is congruent to 1 mod 4, you can always write it as a sum of 2 squares. That's the more interesting part. Now, suppose P is P is equal to -1 mod 4. First, suppose P is -1 equals, say, -1 mod 4. Now, suppose P equals A squared plus B squared. It's a sum of 2 squares. And we show that it's not possible. Now, I take little a. A is congruent, or you can say A is equal to 0 or 1, or you can say in words 0 or 1 or 2 or 3 mod 4, as we know. When we square this congruence, A squared is equal to or congruent to, well, 0 squared is 0, or 1 squared is 1, or that's it. Because 2 squared is 4, that's congruent to 0. 3 squared is 9, that's congruent to 1. So it's just 0 or 1. Similarly, B squared equals 0 or 1 mod 4. So now when we add these two congruencies, a squared plus b squared can only be equal to a 0 plus 0, that's 0, or 0 plus 1, yes, or 1 plus 0, or 1 plus 1. Yeah, or 1 plus 0, mod 4. But these are equal to 0 or 1 or 2. Yes, 0, 1 or 2 mod 4. So they cannot, so the sum of these two squares, a squared plus b squared, or any two squares, can never be equal to our prime p, because our prime was minus 1 mod 4, which is the same as plus 3 mod 4. Was 3 mod 4, so it cannot be equal to a squared plus b squared. Okay, that was the easy part. Now the more challenging part. Let us assume from now on that p is congruent to 1 mod 4. We want to show that p can be written as a sum of two squares. How do I do this? Okay. In two steps, and they both require a different new idea. First step, show that there exists an integer m. Let's say there exists an m such that m squared plus 1 is 0 mod 4. Okay, how do we show this? Now the idea is, one way to prove this, which in some sense is there's a little bit of cheating involved, is to use directly the Legendre symbol. Because we know that if p is congruent to 1 mod 4, we know how to compute the Legendre symbol of minus 1. Minus 1 mod p. Minus 1 over p, quadratic symbol is minus 1 to the p minus 1 over 2. But let's not write this, because there is a little bit of cheating involved, and I tell you why. But minus 1 to the p minus 1 over 2. But p is 1 mod 4, p minus 1 is 0 mod 4, is divisible by 4. So p minus 1 is a multiple of 4. So when you take p minus 1 divided by 2 in the exponent, is still an even number. And minus 1 to an even number is plus 1. So indeed, the Legendre symbol of minus 1 is plus 1. It means that minus 1 is a quadratic residue, and it means that minus 1 is congruent to a square. But that's exactly what we said. Minus 1 is congruent to m squared for some number m, which means that m squared plus 1 is congruent to 0. That's a proof. Now that's a legitimate proof. It's no cheating, provided you show in a different way that the Legendre symbol of minus 1 over p is 0, which we did not prove, you see. We didn't have time to prove that. So that's why I said it's cheating from my point of view, because I didn't prove that thing. So I want to give another proof for this thing directly. And I'm not going to use Legendre symbol. I use Wilson's theorem. So let m be congruent to, now the following quantity. P minus 1 over 2, it's P minus 1, the whole thing divided by 2, and this whole thing factorial. Put another parenthesis. Okay, this whole thing factorial. That's the product of numbers from 1 to p minus 1 over 2. Let them be congruent to this. I claim, let's write, claim that m squared plus 1 is 0. It's equal to 0 or congruent to 0 mod p. How do I know that? Okay, let's write Wilson's theorem. That's p minus 1, Wilson's, yes. Wilson's theorem. P minus 1 factorial, right, in the parentheses, p minus 1. Right. Yes, p minus 1, the whole thing, factorial, This is congruent to minus 1. So let's say minus 1 mod p. Now, let's rewrite this as follows. 1 times 2 times 3 times dot 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 time dot 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 up to, let's stop at p at half of this interval, p minus 1 over 2, and then yes, and then what's the next? Well, I'll tell you what. Let's say dot dot dot. Let's say dot dot dot. What's the last one?
P minus 1.
P minus 1. Let's put in parentheses. Let's put the previous one as well. P minus 2 and then P minus 1. P minus 2 and then P minus 1. Now this whole thing is congruent to minus 1 mod P. Now let's observe the following. P minus 1 is congruent to minus 1. So I can replace P minus 1 in this congruence by minus 1. I can replace P minus 2 by minus 2. P minus 3 by minus 3. So I have the numbers from, yes, from right to left, minus 1, minus 2, minus 3. Let's put a minus 3. The previous one, and so on, up to minus what? What's the first one that appears there?
P minus 1 by 2.
Right, it's minus P minus 1 by 2. Let's put that, the whole. So because we have 1, 2, 3 up to P minus 1 over 2 in the first half of the interval, and then we have exactly the same numbers in reverse order on the second half of the interval. Okay. So I see what you did. Very smart. So you replace the product of the numbers of these black numbers by a product of green numbers. That's our number M, right?
Yes.
Now, in the second part, let's not do anything rush. The second part, we actually have the same number M, but because it's still we still have 1 times 2 times 3 and so on, but then we also have some minuses. So it's a minus to a certain power, and then times exactly our M again. Now let's identify first minus to what power? Well, how many minuses we have? How many numbers I have?
Even?
Okay, but how many total?
P minus 1
over 2. So let's write it in this form. It's minus 1 to the, let's write again, let's not write. Minus 1 to the, and the exponent is P minus 1 over 2. That's in the exponent. And then we have, right. And then we have times M, our number M, the green thing, times M on the same row. Yeah, oh, okay. Times M. And then the rest is another M. So it's times M squared. And that's minus 1. Again, so this equals minus 1 mod P. It's congruent to minus 1 mod P. Again, why? That was M squared. It's exactly the same product. 1, 2, 3 in this reverse order up to P minus 1 over 2. Okay, now let's see what we do with this minus 1 to that power. You said that it's even. Let's see why is this even. Because P minus 1, it's a multiple of 4.
4.
And divide by 2 is still a multiple of 2.
Yes.
So the exponent is indeed even.
Yes.
So now if I take minus 1 to an even exponent, it's plus 1. So we can remove this from there. Let's just take it out. I have M squared is congruent to minus 1. Let's just add the 1 on both sides. And I have M squared plus 1 is congruent to 0. Okay. So we got our M. We said that there is an M. That was our claim. There is such an M. So that M squared plus 1 is congruent to 0. Good. Now, what this means is that our M squared plus 1, it's a multiple of P.
Yes.
Now, M squared is a square.
Yes.
1 is a square.
Mm-hmm.
M squared plus 1 is the sum of 2 squares.
Yes.
But it's not necessarily equal to P.
Mm.
I need to find the sum of 2 squares that's equal to P. Now, so now the second idea. Take these numbers, multiples of M. These are M, 2M, 3m up to, not all of them, up to about square root of p. Square root of p is not an integer number, right? Yeah, instead of putting, yes, let's maybe write on another line. Maybe can you write? You can write on the line above, right?
Yes.
Let's say let k equal integer part or the floor of square root p. The square root of this square root of a prime number is not going to be an integer number because the prime is not a square.
Yes.
Integer part. Okay, there's the integer part. So what this means is, so k, so let's see. So
up to k.
Let's write one more line, an inequality. So k is less than, so k is less than square root p, but k plus 1 is strictly larger than, right? K plus 1 is strictly larger than square root p. That's the property of the integer part. That's why we took the integer part. I didn't say let's take a very small number k that's less than square root p, because if I take a very small k, its square may still be less than p. No, I want to take the largest possible k, but such that k is still less than square root p.
Yes.
So the next, so I took k to be the largest. So that means if I take the next integer number, that's k plus 1, it's too big. It's bigger than square root p.
Yes.
All right, we keep this in mind. All right. So up to k times m. I don't want to go over square root p times m. K times m. Take these numbers. Take the remainders. Take remainders modulo p. And now we have a claim. There are two remainders. Two of these remainders. Such that the difference is less than, such that their difference is less than square root p. Less than just square root p. Okay. Actually, I need to put one more. You see, when I take these numbers m to m, let's start with 0 times m. So let's start with 0 and then m. 0 comma m. Okay. Now, how many numbers I have? I have k plus 1 numbers. K plus 1 is larger than square root p. Now just think about this. I don't care where those remainders are, but those remainders are in the interval from 0 to square root p. Now, if you take more than square root p numbers, no matter how you try to arrange them, two of them will be a distance less than square root p.
Yes.
For instance, if I took what is 100 square, 10,000. No. Okay. You can write if you want, but I was thinking about it instead of writing. Suppose I have because my prime is not 10,000, but I'm just saying, I take the interval from 0 to 10,000, or from 1 to 10,000, or from 1 to 10,000 minus 1, or whatever. 10,000. It's an interval of length 10,000. That's 100 times 100. But I have more than 100 remainders because I have more than 100 numbers above. Oh, by the way, we know that all these remainders are different because they are part of our sequence from the previous proof, the green-red thing.
Yes.
Because they appear on the row of multiplication by my number m. You see 0 and 2 and so on. Okay, so these numbers have different remainders. But the remainders cannot all be far away. They cannot have this enough distancing between them, so to speak,
Yes.
just because you have more than 100 numbers in an interval that's 10,000, that's 100 times 100. So some of these distances will be less than 100, which is square root p. That's the basic. It's the so-called pigeonhole principle.
Pigeonhole principle, yes.
Yeah. I mean, you have a number of holes, like a number of intervals, and you have more pigeons. So no matter how you put them, and two pigeons you have to put two of them in the same hole.
Yes.
Pigeons, rabbits, whatever they are. Okay.
Yes.
So let's denote this number somehow. Let's say a times m. Okay, so little
R1,
a times
R2.
R. Yeah. Okay, R1 minus R2 is, say, an absolute value less than square root p. So the absolute value of R1 minus R2, because I don't know if R1 is larger than R2, and so on. Good. Now, suppose R1 was the remainder of, let's write in words. Suppose R1 was the remainder of it's a multiple of m. Little a times m, because it's one. And R2 was the remainder of, say, little b times m. Okay. So AM is congruent to R1. AM is equal R1 mod P. And BM is equal R2 mod P. Now, it looks it's getting more complicated, but we're almost done. So we have to see what the idea is. Denote now. I introduced two numbers, U and V. And believe it or not, there's nothing to do with the problem, but eventually it's going to be these two numbers that will give us the solution. U squared plus V squared will be equal to P. Now, what are these numbers? Denote U. Oh, okay. Denote U equals B minus A. And V equals R1 minus R2. Okay. Now, okay. So
Hello?
now I claim the following. First of all, if I look at those two congruencies that you wrote the line above, which is AM is congruent to R1 and BM is congruent to R2, let's subtract those congruencies. So let's, there's no claim, it's clear. So when we subtract the congruencies, what we have is, yeah, but let's say it's, I don't know which one is larger, A or B. Say B is larger than A. Okay. Let's write in words, because it doesn't matter, it's the same proof. Say B is larger than A. But it's not a claim, it's an assumption. So let's remove the word claim. Sorry. Okay. Say B is larger, just to make a choice. It's exactly the same proof if A is larger than B. Say B is larger than A. Then let's take this difference. Then BM, but let's write in another line. BM minus AM little b. BM minus AM, this whole thing is equal to what? Well, we subtract those two congruencies. 2 R2 minus R1. And it's not equal, it's congruent. Mod P. Mod P. Okay. Now, let's write another line. We take M as a common factor. So it's B minus A. So it's M times B minus A. That is equal to R2 minus R1 mod P. So now let's have a look at the definition of U. U is equal to B minus A. Oh. So it is exactly U times M. M times U or U times M. M times, let's write it as U times M. Doesn't matter. U times M. is equal to or congruent to V, exactly, because mod P. Good, so far so good. Now, before going any further, let's recall on another line. Recall. 0 is less than, strictly less than, 0 is strictly less than which one? U, because U is B minus A. We said that B is larger than A.
Yes.
Because we got two different numbers, A and B, two different remainders. A is not the same as B. These are two different remainders that are close to each other. Pigeonhole principle. Okay. So U is not 0. And it's strictly less than, let's see what. Let's continue with this inequality. U is strictly less on the same line. Then square root P. Square root P. How do I know that? Well, but because U was equal to B minus A. A and B are two of these numbers, 0, 1, 2, up to Km on the first line on this page. You can see the numbers 0, M, 2M, 3M, Km, right? So A and B are numbers from 0 to K only.
Yes.
Because there's two of those numbers are our A times M and B times M.
Yes.
So A and B are these coefficients that are from 0 to K, but K was less than square root P. So both A and B are less than square root P. So the difference is of these two positive numbers is less than square root P. So we get this. Okay, next line. I don't know that V is positive or negative, right? But I know that the absolute value of V, see, absolute value of V, this, if we see what's this, this was equal to absolute value of R1 minus R2. Because V was equal to R1 minus R2, right?
Yes.
So this is absolute value, and it's R1 minus R2. I put inside the absolute value, and I look at what I know about the absolute value. Absolute value of R1 minus R2 is that line, right? It's strictly less than square root P.
Yes.
All right, so let's write then it's strictly less than square root P. Good, less than square root P. So now let's square this inequality, and I have absolute value of V squared, or V squared is the same. So V squared is less than, forget about, no, not equal, forget about that. Just the square root P squared, that's P. And one more line, the same thing with U, little u. Where is little u? Was strictly positive, but less than square root P. So less than P. And both of them are strictly larger than 0. U definitely is strictly larger than 0, and also V, as we show. Because so on the left, you start like this: 0 strictly less than V squared, and 0 strictly less than U squared. Because if U was strictly larger than 0, and U squared is strictly larger than 0.
Yes.
Okay. Now, let's keep these two inequalities in mind, and let's add these two inequalities actually. And what I get is that 0 is strictly less than V squared plus U squared, right? Both numbers are positive. V squared, not V to the U, V squared.
Sorry.
Yeah. V squared plus V squared, and is less than what? Then 2 times P. Okay. That's the important conclusion, and we have another important conclusion above. Recall that U times M is congruent to V. Can you see that? U times M is congruent to V. So now let's square that one, and I have the congruence. U squared, M squared, plus, it's congruent to V squared. Okay. So now I do the following thing. Let's add on both sides a U squared. So it's U squared plus U squared M squared plus u squared m squared, this whole thing is equal to u squared plus v squared. They're not equal, they're just congruent, mod p. Now let's have a look at what happens on the left side. I can take u squared as a common factor. So let's rewrite this one more time with u squared as a common factor times what? 1 plus m squared. Now this is music to our ears because 1 plus m squared, we know something about this number. Let's see what we know about this number. It's congruent to 0 mod p. It's a multiple of p. So this thing on the one hand is equal to u squared, I mean congruent to u squared plus v squared mod p, but also the left side is congruent to 0 mod p, because 1 plus m squared was congruent to 0. That's why we needed a number m such that m squared plus 1 is congruent to 0. Now we see how this works. Okay. So u squared plus v squared is 0 mod p. But, and now that's the last part of, yeah, u squared plus v squared is a number between 0 and 2p. Strictly larger than 0, strictly less than 2 times p. The only multiple of p in this interval is p itself. You agree?
Yes.
Maybe I say, do you agree? Yeah. So this is equal to p because we just showed that it's a multiple of p, but there are no multiples of p in that interval from 0 to 2p. Strict inequalities. That's why we were careful with inequalities. When we have strict inequalities, we wrote strict inequalities.
Yes.
Success. That's the end of the proof. But I want to see it. Yeah, simple example, quick example.
Okay.
And then we close the video. Let's take p equals 13. All right. What is our m? First question.
M.
What is our? We want to show that 13 is. This is a prime number. Is congruent to 1 mod 4. Right. We will want to write it as the sum of 2 squares, and already know what the answer is, because it's 9 plus 4. But forget about that. P is 13. Let's start with the proof. We found an m such that m squared plus 1 is congruent to 0. Plus 1 was congruent to 0 mod 3. And we had a method. We use Wilson. So let's write this line. 1 times 2 times 3 times 4 times 2. No. Let's write all of them. All of them. This is sorry.
No problem.
6, 7, 8, 9, 10. So then we can all see what actually we said earlier. 12. Now that's equal to, let's put an equal. It's congruent to minus 1 mod 13, modulo 13. Now we are going to replace 12, not on this line. Please write another line.
Sure.
Where you replace 12 by minus 1, you put in parentheses, 11 by minus 2, yes, 10 by minus 3, 9 by minus 4, 8 by minus 5, and 7 by minus 6, and done. So, but put parentheses. While I talk, you put parentheses around minus 6, around minus, because these are, yeah, numbers that are multiplied. That's what we said earlier. We take the first half of the interval from 1 to 12. So the first 6 we leave as they are. And then we have these minuses. So this whole thing now becomes let m, we say let m was equal to what? P minus 1 over 2 factorial, 6 factorial. 6 factorial. So it's the product of numbers from 1 to 6. That's how we defined it earlier. So now we rewrite the last line as follows. It's minus 1 to what power? It's minus 1 to the 1, 2, 3, 4, 5, 6. It's minus 1 to the 6. Let's write it as minus 1 to the 6. Minus 1 is in parentheses. Minus 1 the quantity, minus 1, yes, to the 6 times an m, which is a 6 factorial, and then we see we have another 6 factorial, and then another m, so it's m squared. Again, 6 factorial appears from 1 to 6, and then you have 6, 5,
4, 3 to 1.
4, 3 to 1. It gives another 6 factorial. So that's why we had an m squared. Now, next line, minus 1 to the 6 is plus 1. That's what we said earlier in general, full generality. P minus 1 over 2 is an even number. So minus 1 to the even number is 1. So we get m squared, it's minus 1 mod 3. So m squared plus 1 is 0 mod 3. Exactly. We conclude now that our m satisfies this. Satisfies this. Satisfies m squared plus 1 is congruent to 0. Mod 13. Let's write it. Okay. And I want to do this. I have my m. It's 6 factorial. Now I want you to compute separately on another line what 6 factorial is. It's 720, and we did it many times. Now find the remainder of this. Find the smaller m. I'm not going to work with 702. This is also congruent to what? 5 mod 13. I trust you in general, but I want to see what is the difference. 720 minus 5. I want to see how you, let's write 720 minus 5 on another line. 720 minus 5 is 715. It's 13 times 55. Are you sure about this?
Yes.
Okay, and then we'll ask everybody who watches the video to check using a calculator or just to multiply the numbers. So indeed, let's trust you. 720 is congruent to 5. So then let's work with this number. It's smaller. So let m equals 5. 5. Now, just for us, the next line, 5 squared, I want to compute because maybe I solved the problem already. No, let's write 5 squared plus 1. Yeah. Equals 25 plus 1 and equals 26. You see, it's a multiple. Yeah. Well, in general, when we work with integer numbers and we do equalities, I shouldn't put on the same line congruences because then it's confusing.
Yeah.
So let's just remove this from after 26. Remove. That's no after 26. So 5 squared plus 1 equals 26. Now this is a true equality. Yes. And 26 is 0 mod 13. But it's not 13. So you see, it's a multiple of 13. M squared plus 1. So now we go with our second part, which was the following. Find u and v. Find u and v. Okay, now there aren't many choices for u because u was strict. U is an integer. Right, u is between let's see what we wrote. U is between 0 and square root p. We have it written someplace. Where is u? Yes, right there. In our case, what is square root of 13?
4, 3, 3.
It's 3 point something. So the only choices, that's right. The only choices for u can be 1, because our u was positive. U can be 1 or 2 or 3. What about v? V, we don't know that v was positive or negative, you see? But in absolute value is 1 or 2 or 3. So v can be plus or minus 1, plus or minus 2, or plus or minus 3. Yes, plus or minus 2, or plus or minus 3. All right, now let's see which works in our case. We proved in general that there exists. You see, the method with the pigeonhole principle proves it doesn't give us, a way to find it. But let's check. U equals 1. Does u equals 1 work? Well, what do we check? Let's see. Let's see. Let's write the congruence that needs to be checked. it was, let's write the congruence in general. It was U times M. U times M was congruent, so equal to V mod P. Mod P. Now on the next line, let's write it again with M replaced by 5. 5U is congruent to V mod 13. Now, I take this in order. U equals 1. Well, then that doesn't work because I have, if I take U to be 1, I have 1 times 5 is 5.
Mhm.
I have to take V to be 5. It's not in absolute value less than, square root. V has to be plus minus 1, plus minus 2, plus minus 3. So U equals 1 doesn't work. But we know from the general proof that we gave that one of the others, the other two choices will work. Let's take U equals 2.
Yes.
Works?
5 times 2, 10, minus 3 mod 13. Yes.
Okay, so this works already. Let's say, so let U equals 2. V equals minus 3. Okay, let me see why. 2 times 5 is 10. And you're saying that 10 is congruent to minus 3.
Yes.
I agree with that. So our conclusion after the last part of the proof was that in fact our U and V give us the solution. The U squared plus V squared was equal to P. U squared plus V squared was equal to P in general. And in our case is 2 squared plus negative 3 squared is still 9 is equal to 13. And that's how we got it.
Okay.
Okay, let's close this.